Hello, this is Lecture 2, Part B, Systems of Linear Equations and Augmented Matrices. Let's learn a little bit about matrices. I'm not sure how many of you have seen matrices before, but I think it is important to have. It is definitely something that gets used. It's part of linear algebra. Anytime you have any large systems of equations, you're going to be required to use matrices. They show up all the time nowadays. Uh, many years ago, this wasn't as much the case, but with the introduction of computers and the ability to work with large data, matrices. Um, so let's get going. A matrix is a rectangular array of values written inside of brackets. It's just a way of writing something down. It has a size dimension. Generally, the size dimension is denoted by n times m, where n is the number of rows, so n is the number of rows, and m is the number of columns. So it's the number of rows times the number of columns. That's just how we talk about it, n times m. We also denote each element of a matrix a, I, j, where I is the row and j is the column. Some of this is a little bit easier to see by example. When we talk about the element of a matrix, it's a lowercase letter. When we talk about the matrix itself, it's an uppercase letter. So if we're talking about a matrix A, this is a 1 by 4 matrix, 1 row, 4 columns, with elements A1, A2, A3, and A4. When we're just dealing with one row or one column, we don't need to indicate Aij. It can just be the I or the J. When we're talking about a 3-element column matrix, so this is a single column, there's 3 elements, it's a 3 by 1. 3 rows, 1 column. So that'd be B equals B1, B2, B3. Okay. Now we're going to talk about larger matrices. And generally speaking, another word for the row matrix or a column matrix, a lot of times we'll call these vectors. There are different types of vectors. It just means that it's either a row or a column vector. Column matrix. C. So we're looking at another type of a matrix here. This is a 3 by 4 matrix. 3 rows, 1, 2, 3, and 4 columns. The number of elements is literally 3 times 4, so it has 12 elements. We denote this by, let me make sure I've got something that you can see and that's small enough. So we'll notice the row comes first, so C1, 2, 3. So that's the row 1, row 2, row 3, and then the column. So C1, 1, C2, 1, C3, 1, etc. What you'll also notice is if you go down a diagonal, it's C11, C22, C33. And that's something that will show up a little bit more later. Let's just play around with this just a little bit. This is just a way of getting familiar with it. It's a little bit important to have a good understanding of it. I'm going to write down a couple of matrices, and I want you to consider what they're looking like. So let's say we have a matrix M. Okay, so the first question is, what are the dimensions of this matrix? How many rows does it have? It has 1, 2, 3 rows. So it's a 3 by 2 matrix. So it's a 3 rows by 2 column matrix, a 3 by 2 matrix. How many elements does it have? It has 3 times 2 elements, so it has 6 elements. Then the question is, what is element, if I were to say, what is element M11? M11, remember lowercase, M11, is equal to 1. It's this first element. What is M2, 3? So what is element 2, row 2, column 3? It does not exist. It does not exist. It's a trick question. There is no such element. However, what is element 3, 2? And that is row 3, column 2. That's element 6. Okay. Now, we're talking about systems of linear equations. That's what this chapter is mainly about. Systems of linear equations and matrices. When we're looking at systems of linear equations, the linear equation part is this. So linear equation x1 minus 4x2 equals minus 2. Minus 2x plus x2 equals minus 3. Just an example. Why are we using matrices? Well, we're able to take this linear equation and convert it into a matrix form. In fact, we're able to convert it in a matrix form that's actually very functional and useful for us. We have two parts to this matrix, and that is the coefficient matrix, the constant, and the constant matrix. So this is the constant matrix. Let me redo that. That's too bright otherwise. So the coefficient matrix is the coefficients of x1, x2, and the constant matrix is the constants that it's equal to, which is minus 2 and minus 3. So looking at it a little bit further, we see that the coefficients of this are sorry, I've got a interesting. Obviously, I've got a typo somewhere. I'll have to verify this problem. So the coefficient matrix, there must be a minus 1 here. So this must have a minus here. Let me add that real quick. So there's a minus here. And it's also going to be down here as well. Sorry. So the coefficient matrix is minus 1, minus 2, minus 4, plus 1. The constant matrix is minus 2 and minus 3. And then we kind of smash them together to create an augmented matrix. We smash them together just by kind of putting a dashed line in between them. So we just drop that dashed line in between them and we have our augmented matrix. And let's try a couple of examples of an augmented matrix just so you have a better idea of what we're dealing with here. So I'm going to write out a system of linear equations. I'm only going to use two variables right now. We can do this for any size system of equations. But I'm going to do that for two variables right now. So let's say that we have 3x plus 5y equals 9, minus 3x plus 25y equals minus 1. It's relatively easy to convert this. We have the coefficient matrix, 3 minus 3, 5, and 25. And then we have the constant matrix. The constant matrix is 9 and minus 1. We get our augmented matrix from these, which is 3 minus 3, 5, 25, 9 minus 1. This is our augmented matrix. Now this is something that goes both ways. We can go from having a system of equations to an augmented matrix. we can also go from having an augmented matrix to having a system of equations. So let's say we start out with the augmented matrix minus 8, 7, minus 6, 5, 1, 2. So using this, we can convert this back to its original system of equations. And let's say that the variables are x1 and x2. It doesn't typically how we're going to use them is they're going to be x1, x2. But as you can see from the previous problem, you can use x, you can use y, you can use z. Just for formality purposes and for ease of extension, we use x1, x2, x3. Okay? So this would be minus 8x1 minus 6x2 equals 1. 7x1 plus 5x2 equals 2. So that's how we convert from our augmented matrix to our system of equations. That is the end of this video. We'll come back to row operations in the next recording.